Hello and welcome to our final video on combinations and permutations. If you're watching this because you're in my discrete structures class, this is a topic we look at in class in week 2 and sometimes we don't finish. So this is the third of 3 videos. We're going to start with these last 2 problems we do really show you the difference between a combination and a permutation. This first problem here, you're in a class with 12 students, but only 10 seats. So here I am, the teacher, and I've got this terrible problem. I've got 2 students who aren't going to have seats. So how many different groups of 10 could I seat at a time? And it doesn't matter where they sit, but they get a seat. How many different groups of 10 could get a seat? This is a class where you're just choosing 10. You're not choosing a first one, a second one, a third one. You're just choosing. You've got almost like a bucket of 10 you're making. You're putting 10 students in some sort of think of it as a bucket. Or if I just say, 10 students are going in the room and 2 students are not. There's no particular seat any goes in. This is a classic 12 choose. It's a combination. So combinations are always a lower number than a permutation. Because what the combination tells you is how many different groups can you make. And then, in addition to that, the permutation that we'll see in problem number 4 here tells you, additionally, how many different ways can each of those groups be arranged. And it's almost a multiplication kind of thing, because this formula 12 choose, it's also written like this. This is 12 choose 10, and we're going to see this in the binomial theorem next week. This is really important to binomial theorem. This formula here. N factorial over n minus r factorial. So n is the 12, r is the 10. So this is 12 factorial, and it's not over the 10 factorial, it's over what's left. It's how many I choose, how many I have factorial divided by how many I leave factorial. And then there's also this r factorial here in the formula that I didn't write initially that I should have. This is where that r goes. So what you can see is this is going to give me a 12 minus, that should be 12 minus 10. There. N minus r. 10, 12 minus 10. So I get, I knew it didn't look right. 12 factorial over 10 factorial. How many you choose, how many are left. Notice 10 plus 2 adds up to 12. That's always going to be true in the combinations. The only difference between the combination problem and the permutation problem is this dividing by r factorial. And that's because r factorial is just how many ways you can arrange 10 people. So if I don't divide by this r factorial here, I'm counting the same 10 people multiple times because I'm counting all the different arrangements. This division by 10 factorial says I'm only counting a group as one. It doesn't matter which seat they sit in. So working with factorials, if I have a 12 factorial, that's 12 times 11 times 10 times 9. That is the same as 12 times 11 times, I'm going to write that as times 10 factorial, because 10, 9, 8, 7 would be in 10 factorial. And then if I'm dividing that by 10 factorial, everything on the top is multiplied, everything on the bottom is multiplied. I can actually reduce these terms. Now, if I'm adding, I can't do that. Keep that in mind for algebra. We have some bad algebra that haunts us from time to time. So 12 times 11 over 2 factorial. Well, 2 factorial, you can do this in your calculator too. And in your calculator, in your TI, if you go to the math menu and you go over to the probability, it's like there's like 4 choices in that math menu. Go over, I think it's the 4th one. If you look down a little bit, there's an exclamation point. That's your factorial. It is definitely in that math menu somewhere, so look around. I've learned all my calculator stuff and all my computer stuff by looking around. So this is 2 times 1. Well, again, everything's multiplied on top. Everything's multiplied, so I can reduce it 12 and 2 and get a 6 times 11. And that's a 66. There are 66 possible ways I can choose 10 students from a group of 12. Interesting point here, and we'll see this in the binomial theorem. What if instead of choosing 10, what if I only had 2 seats? So to do this problem, if I only had 2 seats, my n would still be 12 students, and my seats, r, would be 2. But I would get exactly the same answer, because choosing 10 is the same as leaving out 2. Now, I wouldn't get the same answer for permutations, but I would get the same answer for combinations. 12 factorial over r factorial times n minus r factorial. So that's 2 factorial, and this time it'll be 12 minus 2 factorial, which is just the 10 I had before, and you get exactly the same answer. You get 66. So you can either count how many you're taking or how many you're leaving out, either way. You get the same number of groups. So if you choose 10 students, the group of 2 students that's left out is defined. So that's an interesting thing to see, that that there's a symmetry about this combination formula. So let's look at the same problem, only now we care which seat they're in. You have seat A, seat B, seat C, seat D, seat E, and this would be an arrangement. Seat F, 1, 2, 3, 4, 5, 6, seat G, seat H, seat I, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, and seat J. How many different ways can I fill these seats? And a student sitting in seat A is different than that student sitting in seat B this time. This is actually a much simpler problem. This is called a permutation. So I'd have a 12p2, if you're looking in your graphing calculator at those probability menus, and that is simply n factorial over n minus r factorial. You don't divide by how many you choose, you only divide by how many you leave out. And the reason that works is, if you look at this first seat, before I choose any students, how many choices do I have? I have 12. All right, I've chosen a student. Now how many choices are left for this seat? Well, there's 11 left for this seat. I can choose from 10 to the seat, and you multiply all these. It's almost like you can make a possibility tree out of this if you had a really big piece of paper. Times 7 times 6 times 5 times 4. Yay, I get the right number of seats, times 3. And what you notice is I'm missing the 2 and the 1 for 12 factorial. Well, 12 factorial over 12 minus 2 factorial is 12 factorial over 10 factorial. Sorry. Yeah, over 10 factorial. No, that's not right. This is right. So it should be 12 factorial over 2 factorial. Oh, yeah. I did choose 10. I'm doing choose 10, not choose 2. I had the problem wrong. Yeah, if I do choose 10, it's over 2 factorial. It's over n minus r. I want to choose 10, not 2. Sorry if earlier in the video that confused you. You're choosing 10, not 2. So you can see if the permutation, I would get a different answer. But this is just 12 times 11 times 10, etc., 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 down to 2, and the 2 factorial gets wiped out at the end by this and this, and the last number you multiply by is a 3, which is exactly what you see. So it might be easier to remember writing it out like this if it's a permutation, but be careful, because that's not a combination. That's a permutation. When we talked about the problems with sandwiches, yeah, we did just multiply things, but they were combinations because they weren't the same things. It was 2 types of bread, then 3 types of meat, then 5 types of cheese. So they were they were actually more ordered because they were different types of things. And sitting students in an arrangement is like sitting in seat A is different than seat B. So it's like meat is different than cheese is different than bread. So that's why this multiplication of all the choices that are remaining works. And the reason there's only 11 choices remaining here for seat B, let me see if I can, I don't know why it's not letting me write. It's not letting me write, but all the choices for seat B here, there's only 11 because I've already taken one person out and he can't sit in 2 seats. So hopefully that helps you with some of the combination and permutation problems. Email me as you have trouble with the homework, and I'd be glad to answer your questions. Or if somebody, if I get an email that seems like I should make another video, I'll do that too. All right. Until next time, until the next video, or I'll see you in class. Thank you.